lunch, but don't expect lunch.
Där har vi. Okay, finally. So, as we will talk about IP security today. So, what level of the protocol stack are we then? Yep, the internet layer. So that's what we focus on. And on the internet layer you have some protocols, but the main protocol is the IP protocol. If you compare different layers, the internet layer is the smallest layer in terms of different protocols. And that means if we want to put security on that layer, it's really together with the IP protocol then that we need to do that. But we'll look at why we are in the protocol stack, why we put security here. And then we'll look at a standard called IPsec, which is focusing on getting security for IP, and which is actually an entire family of protocols. And that's what we'll look at. So here we are. We have two computers here. They are connected on a LAN end system. Y should be X and Y, I guess, but yeah. Two different end systems. They both have routers that connect them through an internet. And if you look at the communication that we have, there are two different applications on each end system that are communicating. That could be mail or web, whatever. On the transport level, we have some type of transport connection. Could be UDP or TCP or something else, but we have some type of connection here. And that is also end-to-end. But then on the IP layer, the communication is going through the different routers that we have. I mean, at one end system here, we do tell that we need to go to this computer here. But doing that means that we have to pass a number of nodes that have different IP addresses. And things can happen here in these nodes. For instance, that router could actually be a NAT router, which means that we actually change the IP address. So even if IP is in some sense end-to-end, we are communicating with the other side, the other IP address. We do have nodes on the way with different IP addresses, and the IP address can actually change. Below the IP layer, everything is connected with the physical link we are using and the specific network, the physical network that is. So down here, everything changes and it's only link to link. So the IP layer is the lowest level that we can have some type of end-to-end communication and get security. If you go below it, it will be just link security then, part of the way. So let's look at what we have on the IP layer then. The IP protocol, as you know, we have two currently used versions of it, IP version 4 and 6. And this is the header for IP version 4. And what do we have here? Well, we have the version number that tells us this version 4. We have a number of different headers here, which makes IP4 header quite big. One of the reasons why we have changed to IP version 6 to reduce some of headers here. But we have some that are important when we talk about security in this context now. We have the source and destination address. That's where we aim to go. we have protocol here. What does this protocol field do? What does it mean? Yeah?
It indicates the protocol that is contained within the IP packet?
Yeah, exactly. It tells us that what comes after the header here is the payload. And we need to know something about what is that payload in order to know how to deal with it. And that is what this protocol is telling us. It tells us what protocol has forwarded the payload. If we go to version 6 here, let's see, we have reduced some of the headers. We have much more space for source and destination headers, since IP version 6 headers are much longer. And the next protocol is now instead called next header. Why is it next header instead of next protocol?
Because of the fragmentation.
The fragmentation?
Yeah. The stamp on the
That's not complete answer, but yes, it could be part of the answer, because we see here that in the IP version 4 we have information about fragmentation. We have flags telling us if there was a fragmentation, and we have this fragmentation of if we have to split the packet up in different parts. If we look at IP version 6, we don't have that anymore. Now, the general idea of IP version 6 is that you should never fragment, but you can if really needed. And if you have to do that, there is no room in the header to handle fragmentation. So how do you do it then?
local also before sending.
Yeah, we do it before sending, but still, if we need to fragment somewhere on the way, how do we handle it? Because we can't, there's no room in the header to tell that we have done fragmentation. No one remembers? Well, we have something called extension headers. So if we need to do more things than the base header can handle, we have to add extension headers. So the idea is that if we have a big IP packet here, this is the base header. That is what we have here, with just a few fields. And then if we, for instance, need to do fragmentation, then we put in an extension header here that handles fragmentation. And then maybe we want to do something else. We want to do source routing. Okay, then we put in another extension header that handles source routing. And then this next header that we have here in this field here tells us, okay, what comes next here? And in this context then, next header here is an extension header that handles fragmentation. And here you have again the next header that points to, okay, next one is source routing. And then you have a next header that points to, okay, so this is actually a TCP packet now, for instance, or whatever it is, the content. So next header is here because we can actually add more extensions. But the last extension header points to next protocol. Okay, so that's the difference between IP version 4 and IP version 6. We'll come back to that when we talk about how to implement the security. So, IPsec is now the standard for how to get security on this level. And as I said before, it's not one protocol, it's actually an entire suite of protocols to handle different parts of this. And what we try to do is to get different types of security. And because we want to have different options here is one of the reasons why we need actually several protocols. We'll come back to that. So these are some examples of how we might want to use IPsec. The first one, secure a branch office connectivity to the internet. So we have a local network with all our resources, but now we also have a branch office with some computers and some services. We would like to connect these two together so it works as one network. but it's secure even if you have to use the normal internet to connect them. So that's a typical case when you use IPsec. Remote access, we have a mobile user is going around, need to connect now and then to the network to reach different services. Or we want to establish some extranet internets with different partners. We would like to say that some of our systems should be available to another partner, some other systems should be available to another partner, so we extend our network to different partners. And another idea was also to handle, to increase security for electronic commerce. We'll actually come back to that when we talk about payment systems. So here we can see some of these scenarios. We have here a public network that we connect to. Here we have two different routers that connect different branches of our organization. Up here we have a mobile user who's just directly connected to the network. Yep.
What is the advantages of this? What are the advantages? Like, I think we could do all of this with just normal encryption. Or is there an extra advantage why this is needed?
Okay, so the question is what is the advantage? Why don't we just encrypt? Well, part of what we do here is IPsec, but we will encrypt the traffic. But the reason why we need this structure is that we need to have an architecture for decide exactly what level of security is needed for different types of traffic. I mean, we couldn't just encrypt something. We need to control how to encrypt it. And part of this is to decide in what to control and how in different situations. That is a main part of it. That's actually. If we look at some details already now here, we see that here inside one of our local area networks, we have IP packets with a header and a payload. And as long as we stay within our local networks, that is what we have here. As soon as we pass a router here and start to send something out on the network, we typically add more information here. What we do is we encapsulate these packets into a container that makes it secure. And then we send that entire encapsulated packet over the network to the next router, and then it's decapsulated and forwarded internally as a normal IP packet again. This mobile user up here, who's connected directly to the network, need to do that itself, need to create these encapsulated packets immediately, because there is no router that can do it for him. So you see there are different scenarios here that requires different ideas on how to handle the security. But the idea is that anything that goes on the public network here is secured. And security can be encryption, it can be authentication, depending on what we are looking for. So, benefits of IPsec. Well, it's transparent application. We are now below the transport level, which means that the application doesn't need to be involved at all. The application will create an IP packet, and then that IP packet will be secured outside that application. If we talk about security on the transport level, it has to be encoded into the application itself. It needs to know about TLS and how to set up a secure transport connection. If we move up to application level, again, it's even more internal in the application. It really needs to know about the application. We saw this one exception with SSH on transport level where the application didn't need to know about it. So we did some tricks there to reroute the traffic without the application knowing it. But normally the application needs to be involved. Yeah, question.
there a trade-off between selecting which particular protocol we need to secure, or is just a good practice to secure the layers?
So if there is a trade-off between different protocols or different algorithms for encryption, or
Different protocols.
yeah, yeah, there is a trade-off, because I mean there are different factors we can use in order to decide. One is how hard it is to implement. What are the requirements in terms of equipment and knowledge from people working it? We have the overhead that security is giving. I mean, every time we secure something, it will be overhead. It requires encryption, it requires more handshake, we have to add headers, it will be overhead, both in times and how much information we have to send. But it is different for different types of security. So these are, I think, the main factors, how hard it is to implement and how much overhead it will incur for us. So this is the main idea for IPsec, that we can implement it and the application doesn't have to know about it, and even actually the users doesn't have to know about it. So we can give the users security without their knowledge. Some other ideas for IPsec is with routing. As you know, we talked about routing protocols in networking course. And we said that for some protocols you don't have any authentication, for instance, which means that you can set up a router and start to sending in false routing information to neighboring router and disturb the routing of the traffic in the network and so on. If you use IPsec, you can set up secure tunnels between routers. So that is how they need to send their information. So you couldn't set up a rogue router. So let's look at the architecture and what do we have? Well, in this entire family, we have one that is called the architecture first, that tells us about, okay, what is needed here? What are the different components of IPsec? Then we have two different protocols here, authentication header and encapsulating security payload. These are the two main protocols that are used to actually get the security. So all packets that are secured with IPsec is either using AH or ESP, or both, actually. Then we have Internet Key Exchange, because we need to exchange a number of keys in order for this to work. We will use both symmetric and asymmetric encryption. We need to distribute keys in different situations. And then we have this protocol to help with that. There is a number of different cryptographic algorithms, both, as I said, public encryption, symmetric encryption, and hashing that we can use. And then there are some other protocols or standards here as well that talks about how to manage the information, how to control this entire architecture and so on. So there are actually a number of standards involved here. And this is another way to describe this, that we have the architecture here on the top that tells us what we have. We have these two main protocols, ESP or H-head. We have all these encryption authentication algorithms. We have something here called domain of interpretation, which tells us how to deal with different type of traffic. And that will control which protocols, which algorithm we're using in different situations. And we have a key management to distribute the keys. The services then that we can get here, depending on which protocol, which algorithm we're using, are access control. So we can know who wants to connect to a certain site, and we can decide if that should be allowed or not. Think about the mobile user calling in, saying, I would like to connect to a network and access it. Well, in order to do that, we need to prove who we are and that we actually have that right. So access control is one part here. We have something called connectionless integrity. And that is, for integrity, we normally need to have a connection. We need to say establish connection with, say, TCP, and then we can have control of packets that are sent and that they are not lost, that they are resent automatically, that they are not changed and so on. There are things we can do if we have a connection. But IPsec offers something called connection integrity because we are on top of a basic connection. We have some knowledge about the packet that should go. So even if we don't create a normal connection, we can still get integrity for packets. And that is, for instance, that reordering and replay and so on. We get authentication. We can know who created or sent a packet. So data origin authentication. Well, especially reaction replayed packets. Confidentiality, of course, a main service if we encrypt the information. And also limited traffic flow confidentiality. And that is, if we do it like this. An attack against traffic flow, what could that be?
Like manual, for example? Like
Sorry?
putting yourself in the middle of a conversation?
Yeah. If we have two nodes here and they are starting sending data back and forth, someone in the middle here could at least listen into this traffic to get some knowledge about what traffic is flowing here on the network. So traffic flow analysis is just doing that, trying to see who is communicating with what are they sending. Even if the information is encrypted, we can see that what protocols are used, at what time, how big the packets are, and so on. And that information can be part of collecting information before we perform an attack later on. So the problem here with this is that each packet is sent here, and each packet can be inspected. We have a header here, and that header can be inspected. So we know exactly what protocols are used, who are sending to who, and so on. What we can do now is that between these two users here, we put up routers that we send through. And then we establish an encrypted tunnel between them. And to this router, we also connect other users, because we have entire networks behind them. Now, if the man in the middle starts to listen to the traffic now, what can we see? Well, this tunnel goes from the router to router. So what we can see is that, okay, that's a packet coming from this router going here. We don't know where it comes from exactly. We don't know what it contains because it's encrypted. The only thing we see that this is IPsec traffic going between these routers. We can also, if we want to make it even harder, inject traffic here. So we send garbage traffic now and then. And again, the man in the middle couldn't see what is real traffic and what is not. Can only see that some traffic is going here, but they don't know the details of it. So that's what we call the limited traffic flow confidentiality. We don't have entire, because if we send something here, it will be seen that something is sent over here, but we lose most of the details about it. Yeah, you have a question?
Was
Oh.
like the same, we could just send some trash traffic that
Yeah,
just makes no sense basically.
yeah, we can send this extra traffic to lose the information in all the other information, but it's not 100%, but we can do quite a lot. So, another view architecture looks like this, and now we also talk about the different versions that we have. So as you see, we have version 3 of IPsec right now. That's the current version. And of this Internet Key Exchange Protocol, it's version 2 that is the current. So, and is the Internet Key Exchange version or protocol can be used by itself. It's used by other protocols as well, not only IPsec. So that's why it's separated here. They are working together, but they can be used separately as well. We also have some other components now that we see here. Well, obviously we have key exchange information here going on between the iKey nodes here. And between IPsec, we have something called a security association. And whenever we set up a security association, we always set up in pairs, so we can send traffic in both directions. So we have one associated going one direction and one in the other direction. So that's called a security association. Between two different IPsec nodes, we can have actually many different security associations, because one security association, can handle some very specific traffic. It could be that one computer that is communicating with another computer, that is extremely important information. So we have a special security association for that with very high encryption. And then we can say for all the other computers that is connecting to that computer, we can have lower requirements, we can have some other. And then we can say that when you communicate with another third computer, we have another security association. So we can have many different parallel security associations going on. And to handle that, we need this database here of security associations. These are current associations that have been negotiated and are used right now. So whenever a packet comes in or is going out, we need to check which security association should it belong to. And then based on that, we can decide exactly how to handle that packet. We also have a policy database up here that is outside, a little bit outside, but it's part of IPsec. And that tells us if there is a new packet coming that we don't have a security association for, we need a policy to describe, well, how should we deal with this packet now? And the policy can say, well, just drop it, or it could say, okay, we need to negotiate a new security association here, which means that we have to kick on back to key exchange protocol to exchange some keys, and then we have to ask IPsec to create that security association, and then we put the information in the database. So now it's a current association. So this policy database is something that is quite stable. It tells us what type of security we should have, while the security database, association database, is always changing depending on what actual traffic we have right now. To make it a little bit more complex, we also have two different modes. We have something called transport mode and tunnel mode. And these two different modes actually protect different parts of a packet and in different ways. So as you see, in transport mode, we encrypt and optionally authenticate IP data, the payload of an IP packet. but we don't protect the header. In tunnel mode, we encrypt the entire IP packet. So even the header, which means that we also will protect the header. And to be able to deliver the packet, we have to encapsulate it, put it into a new IP packet with a new header. Otherwise, if we send it out on the internet and the header is encrypted, of course it would just get lost because no one would be able to know how to deal with it. So that's why we have to add a new header. Anyone on the internet now can only examine the outer header. The inside header and the inside packet is encrypted and secured. While in transport mode, a manual miller can actually inspect the original header and get some information from it. So you can say that tunnel mode is more secure in some sense then, because we protect the entire packet, but it also gives more overhead. And in some cases, transport mode is the only thing that is really useful, because and we'll come back to how we use the different modes here. So both modes are used. Yeah.
From the lecture, is it that IPsec only provides security for the content of the packet, not actually protecting it from the best effort of IP?
Yeah, the content is secured in both these. If you use the ESP protocol, because ESP protocol is for security, for confidentiality. And that is handled in both these. But if you're only looking for authentication, then you don't encrypt the content at all in either of these modes. So it really depends on what you're looking for. Well, actually in tunnel mode you would encrypt all anyway. No? Well, we'll see. So, but it's not always that you encrypt the payload. It depends on if you want confidentiality or not. So here we can see all the different options we have here. We have the authentication header and we have a encapsulation security protocol. These are the two main protocols. ESP can be used with or without authentication. So you have ESP without authentication, you have it with authentication. So with authentication header, you will only get authentication. Here you will only get confidentiality. Here you will get both confidentiality and authentication. So you can ask, well, why don't we just use the ESP protocol, which can give us both confidentiality and authentication? Why bother with a protocol for authentication only? And the reason is that there is a little bit of difference in the implementation. So in some cases it might be interesting. Although I can say that authentication header protocol is not used that much today, but it is still an option. So we have these three different ways we can handle the packet, and then we have the different modes here. So in all, we have actually 6 different options then. And here you can see what is handling. So in transport mode, we authenticate the payload and selected portions of IP header. And if we use IP version 6, also the extension headers. Why only selected portions? Why don't we authenticate the entire header? Well, what does authentication mean? What do we need to do to authenticate the packet? Sorry?
To match the identity with the sender or receiver.
Yeah, but what type of technical solution do we have to get authentication for packets to send, for a message that we send in general?
Max and hashes.
Again? Yeah, message authentication codes. We need to do a hash over the content and then calculate the message authentication code and add that. That is the general method of getting authentication. So the question is, why do we do that only on some part of a header, not the entire header? Yeah.
Maybe some parts of the header change at some point. Like
Exactly.
The IP address of the target can change if it goes through multiple layers of the company, for example. And if it would change, and you would check if the header is still the same, it would always fail.
Yeah. Some headers can change during the way. And any header that could change on the way needs to be excluded from the computation. Some headers will stay without changing. An obvious header that will change is time to live in IP version 4. Each time you pass a route, it will be decreased. So that can never be part of it. But you have to think about for each header, could this potentially change or not? In tunnel mode, we can authenticate everything because the packet will never be changed during transmission. We take the packet and then we put it into a new packet. And the content part of that will not change until it receives the other side. It's an outer header that is added, that will change, but not the inner header. So again, the entire inner and portions of outer header can be protected. If we compare that with the ESP with authentication, here we don't do anything about the base header or in tunnel mode the outer header. Here we only authenticate the payload. So we actually authenticate a little bit less with ESP with authentication compared to authentication header. And if we do the normal ESP, which means that we have to encrypt the entire information then, well, in transport mode, we encrypt the payload. And if you use version 6, we can encrypt some of the extension header based on what they are. In tunnel mode, we encrypt everything, payload and header, and then again put a new header that is not encrypted then, of course. So there are differences for each of these combinations, exactly what is protected. So here we can see the typical implementation of when we use transport and when we use tunnel mode. Tunnel mode is typically used in this situation. We have different networks that are connected to each other. And at the end of each network here, we have a router. So that router implements IPsec, and then we put up these virtual tunnels through internet to the other sites here. And anything that comes from the local network that goes to the router will be protected by IPsec and then sent encrypted through these tunnels to the other side. While traffic within these networks are not encrypted then. So we see that the tunnel ends at the edge of the networks. Up here we have a transport session that goes from one node to another. So the reach of transport mode is typically end-to-end, which is in some cases an advantage then. Because say that in this network here, we actually have an insider that is doing an attack on the network. Since the tunnel ends at the edge of a network, the traffic here internally is not protected with tunnel mode. But if we use transport mode, it will be end-to-end, so it will be protected all the way until that last computer. So that's the reason why we would prefer transport mode sometimes, because it goes further, it goes end-to-end. But of course, the downside is that now the end nodes need to know about it, while they don't need to know about it in the tunnel mode. So we said that we negotiate security associations. We have a database with currently active security associations between different IPsec implementations. Each security association is defined by these parameters. We have something called a security parameter index, which is just a random number we create when we create a security association. It's the destination IP address, the other side that we are communicating with, and an identifier of what protocol we're using, if we're using AH or ESP. And then we have a number of fields associated with each security association to manage it. We have a sequence number, so we can know about all the packets and where they belong in the sequence. We have an overflow here, so we can handle if we reach the end of it. Then we have to renegotiate actually the security association. That is needed because we have a limited size of that field to handle it. We have an anti-replay window, so we don't accept old packets. We have information about the protocols we're using. Can be AH or ESP or both in terms of how we would like to set them up, because there are different variations for it. We have a lifetime of a security, so we can decide that from the beginning this should live for 1 day, and then we have to create a new one if we want to continue. The mode, tunnel or transport, and the path MTU. What is the path MTU? Maximum transmission unit, yeah. And what does that mean?
The maximum size of a packet.
Yeah, the maximum size of a packet that we can send end to end. And of course we check that when we create a security association, we check how big packets can we send. And then we note it here because we don't want to need to fragment packets. Since they now are encrypted, if they are then fragmented, it would be a mess. So we would like to avoid that at least. So we know that if we send packets below this, normally they would live through. But we can't be sure, of course, because packets can be rerouted any time by the network. So it could actually pass a network with a lower MTU, and then it would be fragmented. So we can live with that, but we would like to avoid it.
So that means we use that only for IPv6, right?
No, we do that for IP version 4 as well, actually. We avoid fragmentation here if we use IPsec. And this is what a security policy database can look like. So the idea with this one is that we should have a rule set to decide how to do with different things. So for instance here it says that UDP on port 500 going from a local machine here to any remote on port 500 should just be bypassed. It shouldn't be protected at all. It should just go out as they are, without security for IPsec. And that is the Internet Key Exchange Protocol. Of course, we need to be able to do that type of negotiation because that is what we use in order to set up a security association. So that couldn't be secured by IPsec. So that's why it bypassed. We also bypass ICMP messages because we need to be able to report and get error reports from around the network, even if they are not secured by IPsec. A router on the way could have to drop a packet and inform us that it's dropped. We need to get that, even if we have no security association with that router. But then we say that, okay, all the other protocols, from this machine to a certain other machine, should be protected with ESP. So whenever we communicate with this one, it has to be secured with ESP. And then we say that, oh, well, actually this is an entire network here, as you see, a C-class network. And then we say that TCP traffic between this computer and another computer using port 8443, so that would be a web server then. If it's 80, we should protect it with ESP. If it's 443, we should bypass it, because it will already be protected then with TLS. So it's no idea to protect it again. It would just be the waste of time. So, and so on. And we can very finely decide exactly what computers should be protected with what, and what we should bypass, and what level of security and so on. So to create such a policy, of course, important in order to get security. We need to know what type of traffic we have and how to protect it. And at the end we say that all the other is just bypassed. So if this machine here would like to connect to random web server somewhere that we don't have discussed before, no other rule will match but the last one, so it will just go unprotected out on internet. So this is a policy that allows a lot. We could have said that anything that is not here, it should be dropped instead. And then only protected traffic would be allowed. Okay, let's take a 10-minute break here before we continue. Well, that is really up to us to decide on what layer to put it. It could be that we do it on all layers. But it could be that we only do it on one layer. I mean, say that you do on application level, you are securing your email with TCP. Then you encrypt your email, right? And then you send it out on internet. Maybe you have connection with an email server somewhere, and you connect a transport contact with TLS, for instance. That will mean that you encrypt it again using TLS. And then you might have also an IPsec connection that is protecting the traffic between those two machines. So then it would be encrypted again. But that would be, I mean, you would lose quite a lot of performance if you do it that way. You only need to encrypt it one time. So when you implement it, you should know, okay, where do I protect this type of traffic? And for instance, you have this rule here saying that the row, the fifth row, they say that if you already have protection here with the web server of 443, we don't protect it on this level. So we try to be smart and make sure at what level you can protect different things. And sometimes we might want to actually protect it so because we increase the security, but you should know it when we do it. It will be slow, yeah. So go
That's a given now. I'm just gonna say I'm fine. But a little hysterics, exhausted as hell. Other than that.
Aber ich plane nächste Woche dann ganz.
Ja, gerne. Okay. Wenn gerade Zeit, das können wir gerne. Das können wir mal kurz tauschen.
Warte.
Ja, klar.
Was ist klar?
Kein Stress.
Du hast auch deutsches Netz.
Ja, ich habe deutsche und schwedische Nummer, also ich bin da ziemlich offen, aber ich würde eher fürs
Ich habe
Deutsche.
nur ein deutsches
Ja,
Netz.
was? So, für deine eigene Nummer. Was ist mit deinem Entschuldigung.
It's possible and she is smart.
Okay. Achso, welche? Ja, Kletterbanken. Ja. Ich habe eine Flagge. Okay, was?
That's okay, we're indoors, they can't hear us.
Duelsen, Nachteil. Ich
Dann gib also deine Nummer.
Ja. Also ich habe jetzt umgestellt. Nee, das ist die deutsche Nummer. Die schwedische weiß ich gerade selber nicht.
Aber ich bin am Montag bis Samstag in
Yeah, because I was thinking there's a lot of border courses. I was thinking maybe raise some border courses and then like that.
Gerne in der Bib oder
I saw the deadline was
also da wäre ich echt offen. Ja. Super.
Dann haben wir die nächste.
Ja, heute ist die Einführung in das. Achso, ja. Deswegen. Und die nächste Vorlesung ist dann am Montag.
Yeah, yeah, yeah. But who's gonna be the governor?
Yeah, but still, I mean,
I don't know. I've had a spell it.
no.
Right, let's start again then. So, this shows the type of processing that we go through then for a packet. Really just sums up what we just talked about. So here we have for outbound packets. So this is a packet now that comes from an application. It's already passed the transport level. It have gone down to the network level. We have created an IP datagram. And now we're ready to send that datagram out onto the network. Now IPsec intervenes here and says that, okay, look in the security policy database if we know about how to handle this packet. If we don't have any match for it, we just discard it. If we do have a match, then we check what that policy says, and then we go to our, well, the policy can say bypass. That means we just forward it datagram without any change at all. Or the policy can say discard, or we can say protect. So this is where we actually use IPsec then. So then we go down here and we search if we already have a security association for this packet. If we do, well, then we process it according to that security association with AH or ASP, and then we forward a protected packet now. If we don't have a security association, well, that means that we have to create one. So now we kick in the Internet Key Exchange Protocol that creates it, and then we go back up here, and now we can apply it, and now we can process it and send the packet out. And on the inbound interface then, from the bottom here we have a packet. We check if it's a normal IP packet or if it's a packet protected with IPsec. If it's a normal, again, we can check the policy for inbound traffic to see if we should discard it or if we should deliver it upwards. So in some sense, this works a little bit as a firewall implementation as well, because we can check the inbound traffic. If it should be protected, then there should be a security association for it already negotiated. If not, well, then something is wrong here, and then we just discard it. But if typically we find a match here, and then we process it, decrypt it, check authentication, and then we deliver the original packet upwards. So let's go down into the details a little bit. So let's start with the AH protocol. So this is what we have before we apply authentication header. In our IP version 4, we have an original IP header, and then we have a payload. And here we just also added some detail, because we say that the payload is actually a TCP segment. So we also have a TCP header here. But this is the division here between the IP header and the payload. So the TCP header is part of a payload. In IP version 6, it's a little bit different then, because we have the base header, and then we can have 0 or many extension headers. And then the last extension header points to the payload. So again, this is the division for the payload. And again, this could be a TCP segment then, and the data for it. Now, if we apply transport mode, this is what happens. In transport mode, we said that we will work with the packet we have. So this is the packet we have, the payload, and this is the original IP header, or IP, yeah. What we do now is that we actually insert a new header between the IP header and the TCP header in the. So if we look at how IP version 4 looks at this header, it actually looks at it as part of a payload, because this is still the division between the IP header and the payload. So IPsec is seen as an payload protocol. So this would of course increase the size of a packet a little bit, because we need to insert this authentication header here. In IP version 6 that is not the case, because IPsec was delivered or developed together with IP6, but after IP4 already existed. So for IP version 4 we didn't have any choice. We needed to look at IPsec as just part of the payload. But for IP version 6 we can actually include it in part of a specification for IP6, which means that we have a base header, and then we have some headers, for instance this hop-by-hop destination routing and fragment, so we have some headers. And then we have the authentication header as just one of many possible extension headers for IP version 6. So it's actually part of the header. And then there are some other headers that can come after, and then this is where the payload starts with a TCP header from a transport layer. So that's a big difference for how we have implemented it, since we developed IPsec together with IP versions, IP version 6. In tunnel mode, well, now we take the entire packet and encapsulate it, put it into a new one. So here we have the original packet, datagram with the header, and then a content with a TCP. And now we put an entire new header on top of that. So this is the new header, IP header, and we also again have to insert an authentication header as part of a payload of a new outer packet. If we go back here to the transport mode to see what is protected, we see that here we authenticate anything but the mutable fields, the fields in the header here that could change. Same for IP version 6. In tunnel mode, again we authenticate except for mutable fields in the new header and everything coming after this point. And the same for IP version 6. This is how the protocol or the packet format is. Next header here points to, well, if it's, we can look at this one. If it's IP version 6, the next header points to the TCP then, typically. Oh, sorry, it's actually better to look at this one. Here we point to the TCP header. In IP version 6, next header here points to, well, there could be other extension headers that we point to, that then later on point to TCP. So it depends on if it's version 6 or 4. So that's the next header. Then we have the payload length, which tells us, okay, the payload. And what is the payload? Well, in terms of authentication header, we have this authentication data, that is the payload. And what is the authentication data? Well, the authentication data is this MAC code then. So that's the payload. And then we have a security parameter index, so we know this random number we created when we created security association, and the sequence number for this. This is variable because it depends on what authentication method we're using, what hash algorithm. I think we already covered that. And then we take the ESP then. So now its idea is to encrypt the information instead. And possibly also do authentication, but encryption is always there. So if you look at the packet format, it looks quite similar. We still have a security parameter index and a sequence number, but we do have something more here. We have an initialization value if needed, depending on what type of value we're using. We have a rest of payload data. It's variable. What could the payload be here? We said that for AH, the payload is the MAC code. What is the payload here for ESP? Yeah, exactly, the packet. Because ESP should give confidentiality, so it's everything, the entire packet, or the payload depending which mode we're using. But this is the entire original payload at least. That is here, down here. So this is quite big then. And then after that we have also some headers. So actually we encapsulate in all the original packet inside the header here. We have some padding, optional and variable, to make it even size. We can also use this padding to help with this traffic flow analysis problem, because you could just add random data to make a packet look bigger than it really is. And then we can point to the next header. And then if we're also using authentication, we have that at the end here. This is the MAC code at the end. So here we have encrypted data, and this is the optional MAC code. So that makes it a little bit more tricky on how we see the data here. So now again we have ESP with encryption and authentication. So here we do both. This is now transport mode, which means that we have an original IP header and we don't change that. We don't even authenticate it. So that is left untouched. Then we have to insert the ESP header. And actually the ESP header goes all the way until we have the ESP trailer here with padding data and possibly also the MAC code. And then it ends. And inside the header we have the encrypted original datagram. If you look at version 6 then, it's a similar situation. We have a base header, we have some extension headers, and then we have a ESP as another extension header. And then we have the original datagram here, which is now encrypted, the trailer, and an ESP authentication at the end here, if we use that option. In both these examples, we see that authentication does not extend the outer header, and it does not extend the outer header or some of extension headers for IP version 6. So that's the difference between the ESP authentication and the AH authentication. In tunnel mode, well, that means we have to encapsulate the packet into a new packet. So we create a new header, and then we insert the ESP header right after that. And then we have an entire original IP header and everything in the packet as part of our payload now. And for IP version 6, again, similar situation. We start with base header, extension headers. These are new, a new header. And then we have ESP, and the content part of it is the original datagram with original header. So if we use the tunnel mode, that means when we go back to this here. If you use the tunnel mode, a packet that comes from the internal network here reaches the router firewall where we implemented IPsec. Here we encapsulate it into this new packet here. And then that packet goes all the way, well, to another network or to a host in this case. And here we have to decapsulate it and then pass it on, either directly to this computer or to a computer internally. Are there any questions about this transformation? What do we do? Yes?
Is there a way to hide that we are using the tunnel mode? Like in the picture you just shown us with the connections basically.
Mm.
The router could see that we are using the tunnel mode and could block it. Is there a way to hide that?
So the question is if we can hide what mode we are using. No, we cannot do that because that is told here in the header, what mode we're using. And that part is not encrypted, so anyone can see if it's tunnel mode or transport mode.
Basically, if we're using a VPN or the Tor network, anyone can still see that we are using it, but no one can see what we are doing there.
Yeah, exactly. Anyone that intercepts one of these packets can see what mode we're using. And if it's, then they can also see that if it's transport mode, they see that, okay, this is the end computer that will have this packet, because that is the end of a transport. If it's tunnel mode, we can only see what router it will go to. We don't know how it will be forwarded after that. So here we see from a protocol stack point of view, what is happening here. So here we have transport mode to the left here. An application creates data, puts it into a TCP segment, adds a TCP header, pushes down to IP. IP adds an IP header. And then IP is intercepted by IPsec here. And then if a policy says that we should protect it, we insert this ESP header inside here. We still use the original header, and then we perform the authentication on the data here and add these trailers here. And in tunnel mode, well, we start with data from application. The TCP header is added by the transport layer. We add the original header on the IP layer. And then IPsec intercepts one here. Say that, okay, we actually need to encapsulate this. So we protect it, and then we put it into a new IP datagram. So we, in some sort, we push it back to the IP layer. And then we forward this one, because now it's protected, so it's not intercepted again. And the new IP header here will tell us where it should go. This is still only part of a protocol stack, of course, because, as I said here in the break here, it could be that the application here decides that, well, we should also use TLS here to protect the traffic. And that would mean that we have to add some TLS layers here with authentication, where the different protocol formats for TLS, and the two different levels here. And then it could be that we are using, well, what other things could go in here? Well, we could do multi-routing perhaps, and use some type of multi-routing protocol. We could use a streaming protocol for streaming video, but need to add something. And below this, we have some type of protocols for the link. Could be added in a PPP header, or we can have an Ethernet header for going. So I mean, There are lots of headers that is going, a lot of processes as the data is going through the protocol stack before it actually sent out to the net. But you already seen this when you do the Wireshark. Then you take in a packet, and then you can examine all the different headers on different protocols on different layers. Or you can just focus on one to see this data. Okay, so this is the basic. Now let's make it a little bit complex. Well, actually, it is quite complex already, but what we can do is also that we can actually combine security associations to make it even more secure. And we can combine them into what's called bundles, and there are two different types of bundles. As you see, there are transport adjacency, refers to applying more than one security protocol to the same IP packet without invoking tunneling. You can only do this twice or one time, so you can invoke it by both using ESP and then also authentication headers, so you can combine these two together. After you've done that, you don't have any more protocols to choose from, so you can only do that once. Then we can have that is called iterated tunneling. Refers to application of multiple layers of security protocols affected through IP tunneling. And that you can do really for how many times you want. You can add a tunnel to a tunnel into a tunnel. You can add as many layers of security you want with tunneling.
Why are you that for security?
Yeah, why would you want to have several tunnels? Well, we'll see an example of when it makes sense to have tunnels. In general, you can say, well, if we add a tunnel into a tunnel, it will be even harder to attack because you have to break down each one separately. Each tunnel would have different keys. You can have different encryption algorithms, which means that someone attacks, you have to break into each tunnel as a separate task. So it would give you more security, but also more overhead, of course. Yeah. Yeah.
Like we are tunneling through different routers, and if we don't trust the routers, because for example we're in China or something like that, then we could use that so not even the router knows where the package came from and doesn't know where it goes to, because there's a tunnel between through that router, and so no one knows where the package came from.
Yeah, we can. And one tunnel could end somewhere where we don't really rely on the person who's running that. So we put another tunnel in that tunnel to reach us further. But normally you do rely on the people who's running the endpoints of tunnels, because you need to negotiate keys with them and so on. So you have some trust in them typically if you use IPsec. There are other types of tunneling that doesn't require that. So let's see that they are in the standard. I talk about 4 different cases for making these bundles. So this is the first case. One or more security associations end to end. And more here is really 2 then. So 1 or 2 transport associations end to end. So it can be an ISP within an AH or the way around. Case 2 is the simple case of just a tunnel mode between 2 gateways. So the traffic within the local networks, either side of the tunnel, is not encrypted at all then. So this is the simple case that is used in many situations to set up these virtual tunnels over internet. You as the network administrator, you set them up in the gateways. Your users in your network doesn't have to know anything about security, or the application doesn't have to know about it. All the security is in the gateways. So this is a typical way to set it up if you have different branches, for instance. Then we have a combination of the first 2. You have a tunnel between your networks, but you also would like to add some security because you are not sure that there could be an insider in one of its networks. So you also have a transport end-to-end. So end-to-end you encrypt and or authenticate one or two association, and then it's added into a tunnel when it goes out on the internet. So here's a combination of transport mode and tunnel mode then. And the fourth case is similar to the previous one, but with the difference that the tunnel ends at the host here, because this is this remote worker. So first, the remote worker creates a tunnel between his own machine and the router to the network he connects to, and then within that he creates transport security end-to-end. So all of these are possible scenarios, all are used in different cases. It really depends on your situation which one is best. Key management is needed here. All the different nodes that would like to take part here need to have key management. And in this situation, you need to have control of all the different nodes somehow. If you compare this with TLS, in TLS you can set up a connection with anyone on the internet as long as you trust the certificate. You don't need to know about that site beforehand. But with IPsec, you need to have control of all the nodes. So IPsec is not a general protocol for general security. It is a protocol for an organization to protect its traffic on the network. So we need to be able to generate and distribute keys of different sort to all the nodes. Typically we need 2 pairs of keys, 2 per direction for AH and ESP. We need 1 key for encryption, another key for authentication. And since we have traffic in both directions, we need to generate at least 4 keys then. And then as I said, we might have a policy say that different type of traffic should be secured with different security associations. That means we have to generate new keys for each security association. So there could be lots of keys that need to be generated, handled here. And we should use session keys. So we should have unique keys. Each time we create a new security association, there should be new keys. So we couldn't rely on simple ways to distribute keys. We have these 2 options. We could actually handle it manually. With manual, we need to physically configure each device manually to make it possible to take part in the network. Or we can do it with some automated key management, and that would be the IKE then, to create these keys automatically whenever they are needed. And that is really what you need if you handle an organization with more than just a few nodes. So this internet key exchange is really a combination of 2 other protocols, which is called ISAC-MP and Oakley. So together these 2 protocols form IKE, which is used to create and distribute keys. So this internet key exchange is an automated system for on-demand creation and distribution of keys for a situation when we have lots of users and we are changing the security associations all the time. Again, we have this perfect forward secrecy that we talked about with SSH before. So even if a permanent key is later on compromised, old sessions will not be compromised. Now the Oakley part of the IKE is the key exchange. So the Oakley is Diffie-Hellman with some changes in order to be able to create keys on both sides of a communication. We said that Diffie-Hellman as it is vulnerable to man-in-the-middle attacks. And that is handled then in this Oakley protocol by adding some features here. We added what we call cookies, groups, nonces, in order to make it resistant against man-in-the-middle attacks. These cookies here are information that we generate on the fly. It's based on, as you see, IP source and destination address, UDP source and destination port, and some locally generated secret random value that we create with the Diffie-Hellman. So we generate a secret random, and then depend on where we are, we create these cookies, and that means that these cookies can never be used for any other type of communication because it's tied into exactly our communication situation. We won't go into the details on why that works, but it will make it possible to create keys with Diffie-Hellman and know that the keys we create are actually the two parties that should be creating it. There couldn't be a man in the middle here that we are communicating with. That's what these cookies and groups and nonces are helping us with. We need to authenticate in Oakley. If you talk about Diffie-Hellman, we say that we typically use a certificate in order to authenticate, in order to base that on. Here we have digital signatures using certificates, or we can just use public key encryption. So we can have a public key and a private key, and we authenticate using the knowledge of that private key, but without the support of a certificate. Or we can use a symmetric key encryption. So if we can somehow exchange a symmetric key with some other method, it's not supported by iKey. But if we do have that, we have a shared symmetric key that we know we can use, then that can be based for the authentication here. This is rarely the method that is used then, because that requires an additional mechanism here. So typically it's based on public key encryption for authentication. And then the second part of iKey, the ISAC-MP, that's the Internet Security Association and Key Management Protocol. So this protocol is here to help us manage these security associations that we need to create on the fly. So this is the protocol that is negotiated between the different nodes whenever policy says that, yes, we need to create a security association. Okay, then here is how we do it. So it's a framework for key management, but not key exchange, because that is handled by Oakley. It defines procedures and packets to establish, so negotiate, modify, delete security association. That's the main thing here with ISAC-MP. Depending on key exchange, we can do it manually, or we can use the Oakley. Two phases of ISAC-MP. First, we have what's called peer established bidirectional secure channels. So first we secure a channel between us, so we can exchange information in a secure way. And then in phase two, using that secure communication, we negotiate the different security associations. Of course, there is a package format for ISAC-MP, where we have information about what version we're using, what type of message we're sending, some cookies, again, to help against man-in-the-middle or replay attacks. And then we have the message part here, which depend on what type of message. Also see that we are using this next payload idea, so we can have it as an extension header for IP. Exchange types. Well, there are a number of different types of messages we can send with ISAC-MP. So depending on what type of message, we have different payloads on. We can say that we are creating association, we are doing some key exchange, we are authenticating, maybe by sending certificates. So there are a range of different types of packet messages that we can send back and forth. The payload is quite complex here because it depends on what we are doing. So depending on what type of message we're sending first, and then depending on what protocol under, if it's AH or ESP, and then depend on what type of transformation. We really have a tree structure that says that, okay, if we want to send this packet, we need to handle it in this way. If we send this type, we have to handle it in this way. So it's quite complex. We won't go into the details for how to create these payloads. We'll just briefly look at this list here. It says that, well, these are the different type of message we can send with ISAC-MP. And for instance, if we say proposal here is the type of message we can send. We propose to set up an security association, and in our proposal we propose some things again about what type of protocol we're going to use and what type of encryption algorithms we're going to use. Further down we can see that we have a SIG type, that is signature data. So contains data generated by a digital signature. So this is part of authentication then. So this is a complex protocol. Luckily, whenever we are implementing IPsec and use this IKE, there are not very much thing we need to do as a manager. We just need to say, okay, we would like to use IKE. And there are some parameters we can say, of course, but we don't have to think about all these details on how the messages are sent and how they are formatted. That is only for if we would like to implement IPsec on our own. And not very many people have done that actually, because we are using libraries already done for it. So there are a few standard libraries that have this implementation. So if you want to go this route, you would have to spend a lot of hours, I can tell you. There are also some exchange types. So these are standard ways to how to exchange the packets, the patterns for what we need to exchange based on where we are. We said that we have these two phases first. We have the initial phase when we set up connection, and then we have a second phase where we actually communicate. And within them we can use different exchange types depending on what type of information we're sending as well. But you see, they are also quite complex. In what we call a base exchange here, we start with negotiating an security association, and then we agree on some things, and then we generate keys, and then we responder back. So we need 4 messages here in order to negotiate one security association based on that we already have an established phase 1 connection here. For identity protection exchange, we need more messages. So the easiest one is just for information. That is just sending one packet. So again, we have the types, and then we have these ways to do the exchange. That's also quite complex. The algorithms for encryption authentication. Well, we mentioned IPsec version 2 first. And for this one, we have a range of different algorithms we can choose from. all that we have mentioned before, different encryption algorithms, and HMAC with different hash algorithms for authentication. For IPsec version 3, they decided to make it much more simple in some way, because they say that we should use AES for encryption. And for authentication, we should use something called AES-based, cipher-based MAC. So actually, both for encryption and for authentication, we are using AES. There are also other cipher suits that are military graded. So IPsec is actually developed with a possible extension to use other cipher secs for military. And those are not even available for other people. So we only know that they exist, and that you can, when you set up an association, you can say that I want to use this other, but we don't know what they are. This AES CMAC, what is that? Well, this is directly from the RFC for it. It says that AES CMAC achieves a security goal similar to that of HMAC, that we already know about. Since AES CMAC is based on a symmetric block cipher, AES and HMAC is based on a hash function, so that's a difference then. But AES CMAC is appropriate for information system in which AES is more readily available than a hash function. So the idea is that, okay, if you're already using AES, why not use it also for the message authentication code? Strictly, if we look at performance, HMAC is faster. So, and hash algorithms are not something that is hard to get hold of. I mean, if we compare hash algorithms with encryption in history, encryption has had regulation and limitations for what you are allowed to export from the United States, for instance. Hash has always been open, available for anyone. So it's has always been more easy to get hold of hash algorithms. So say that more readily available, I don't think that really is a big problem in most cases. But of course, if you want to make a very slim implementation, you can do it without adding a hash algorithm as well here. But it will cost you a little bit on performance. Some limitations of IPsec: cannot provide end-to-end security as system works at high levels. Well, we are so low that we can be. It's quite general. Even if in our policy we can say that we will do different types of security association depend on the traffic types, we can still only apply ESP or authentication header. We cannot go into the application protocol and handle the payload in different ways depending on what type of application is using our service. So it's a very general service in that sense. And if an application have particular requirements, then that is very hard to meet them with IPsec. So we have to think about that it is a service that is at the bottom level. It gives us a good basic protection for the communication, but it doesn't reach end to end and especially up to the application level. Someone mentioned virtual private networks before, and a virtual private network is really a tunnel through a network. I mean, we are talking about that we have some general network here, typically the internet, and then we have different hosts here. And then we create these tunnels through the network, which are encrypted and secured. So that is a VPN, a virtual private network that is using a public network, but with added security. Now, obviously, this looks very much like IPsec. This is an IPsec tunnel. So IPsec is one candidate to set up a virtual private network, but there are other alternatives, and we'll just mention them here. We have something called point-to-point tunneling protocol, that at an even lower level, actually, just below the IP level, we have a PPP protocol, and there's a variation of that called PPP-TP that creates an encrypted tunnel. We can use SSL TLS to set up virtual private networks, because SSL TLS can, especially TLS then, has been adapted to can be used for any other protocol. So as long as we set it up in a way that all the different traffic that we are creating is actually using TLS, we can see that as a tunneling. And there are some VPN solutions that route your traffic through TLS. So it looks like you're actually using our protocols, but you reroute it through the TLS. It does have some limitations, but it's much easier to set up than IPsec. We already mentioned secure shell before. Of course, we can use that to set up tunnels as well. And we have another one called layer 2 tunneling protocol that is actually quite often used in different VPN solutions. If you would like to set up a VPN, you probably have a VPN client on your computer. And then if you go into the settings, you will see that probably a few of these are options. So you can use different options depending on the situation. So depending on who you communicate on the other side, you might use different options here. So VPN is a more global concept, and IPsec is just one alternative to create them. Right, any question now? Yes?
When we talked about the security policy for IPsec, where we have to choose different protocol that we want to implement, does that affect the cost of implementation of
This one, the policy database.
yes.
The cost of no, it doesn't really affect it, because in order to set up a security policy database, you need to already have IPsec implementation done. And in IPsec, you need to have all the different components there. You need to have key exchange set up somehow. You have the ESP and AH. You have the algorithms, encryption algorithms and hashing that you need. So you already have all the tools. The security policy database is just a way to decide how to use them in different situations. And of course, if you say that the policy says that, yes, you need to encrypt using something with a higher key than something else, that will be slower. So depending on what you decide here, of course, you will get some performance penalty on each security association. So if you make it more secure, yes, then it will be a little bit slower. So that is something you have to think about when you write your policy, so you don't make it more strict than needed. And especially things like this. If you already see that, well, this type of traffic is already protected with TLS, adding IPsec here would cost, because then we have to encrypt twice. And if we don't think that that is absolutely needed for a high security, we should avoid it. So we can save some time here, save some performance by having a smart policy. Yeah?
But there could be scenarios where you would do it. You would
Oh, for sure. Yeah, we can have scenarios where we decide that we would like to have encryption in 4 layers, something like that. Yeah. Depends on. Someone says that it depends on your application. It always depends on your application. So yeah, can happen. Right. Now, is there a lecture tomorrow? No. From now on, we have only 2 lectures a week for a couple of weeks. So, meet you on Monday. But you do have tutoring this afternoon and the introduction for the second assignment. So don't miss it. Okay, see you next week.